Space elevators. Everyone knows what this is and is waiting until the first one is built. But why this did not happen yet? Or even why would one build a space elevator after all? The first reason: costs. Launching mass with rockets is incredibly expensive. Even with the upcoming reusability of launching systems and CubeSats, which just reduces the cost per kilogram and making small missions possible also for universities, a space elevator would top this without questions. Since there's neither fuel to be burned up or structure to be thrown away, their only costs are the maintaining and electrical costs for powering the lift. Compared to a rocket launch with around 10,000 euros per kilogram to the geostationary Earth orbit, the space elevator would reduce the launch cost to around 200 euros per kilogram. With this massive amount of cost saving, even the initial cost for building such an elevator of around 6 billion euros will add up very fast. Also, mainly the frequent lifts to geostationary Earth orbit are very attractive. Referring to the first concepts, a space lift would compete with the mass brought into space by rockets too. Depending on the tether strength, more massive payload could be considered to be brought up into orbit. But this construction can also be used to send payload into deep space. Because of the highest point moving faster than a satellite would do on a circular orbit, the payload could just be released and has instantly a surplus of delta V. Why this is possible will be explained later. But how will a space elevator actually look like? The first idea came from the Russian scientist Konstantin Tsiolkovsky in the late 19th century. At this time it was thought about a compression structure, like a 36,000 km high tower to reach the geostationary Earth orbit. Quickly to be proven unfeasible, the construction through a tether came up. With the incoming research results of carbon nanotubes, the space elevator came back alive into their heads. In the most known paper for space elevators from Bradley Edwards, which is a final report under the NASA Institute for Advanced Concept Phase 2, the space elevator is declared as to be possible. Obviously, the main parts making the space elevator an elevator are the tether and the climber climbing it. Looking at the tether, it has to be longer than the 36,000 km to the geostationary Earth orbit. Since the radial speed gathered through the Earth's rotation is slower than the circular orbital speed at points lower than the geostationary Earth orbit, each part of the tether causes the elevator to fall back. What needed is a counterweight, which shifts the center of force exactly to the geostationary Earth orbit, whereas it is actually better to shift it a bit above this point to make sure it keeps up. The best way is to have a heavy space station on an asteroid as a counterweight, since using the tether itself as a counterweight would result in a very long-reaching rope. By the way, at this counterweight, a payload aimed for deep space mission can be released with an immediate excess of delta V. The stress or the force per area the tether has to withstand has its peak right at the geostationary Earth orbit, since at this point all poles of the tether are either pulling down to Earth or up to the counterweight. To still equalize the stress on the tether on each point, it can be thickened whereas more stress is going to be applied. The carbon nanotubes play a great role here, since its usage would mean only a taper ratio of about 1.6 to 1, which just says the width of the tether at the geostationary Earth orbit only has to be 1.6 times wider than at the two ends. Also, this is the only currently known material strong enough to make a space elevator possible, which could lift some variable mass of payload into orbit. Depending on the final width of tether, variable means about 5 tons and upwards. However, to make the lifting of such mass possible, the tether would have an own weight of several hundred tons. It is of course not possible to launch hundreds of tons into the geostationary orbit at once. So either way, we have to develop a joining method with the same amount of stretch applicable as to the tether itself, or we launch a very thin and therefore light one, creating a space elevator and lifting with light climbers one fiber after another to fix it to the counterweight station. In this way, also a high redundancy of tether fibers can be created in the case of material failure. Another important part is the climber. It has to be very light and stable to carry all the payload, and its driving system has to be powerful enough to lift all this mass, starting from the ground. The driving system would be some kind of roll system, through what the tether is threading through to get enough friction to hold on. Since either chemical propellant or batteries are too ineffective as fuel in terms of mass, the best way is to have an energy receiver system mounted on the climber. If the climber is high enough, solar panels could work out, since also the acceleration needed to keep the climber velocity decreases with the height. Until this point, a power beam could be sent from the ground to the climber, which has its focal point on the receiver system. The power beam source had not even to be placed directly at the entry point. The only requirement would be a correction system for the elevation and azimuth angle and the possibility to change the distance for the focal point. Early tests and calculations state that such a power beam and receiving system would be feasible to feed the Royal Climbing Driver. Another idea is to implement a power supply cable into the tether, which in turn would make the tether itself heavier. Last but not least, the anchor. Somewhere on the ground of the planet Earth, the tether has to be fixed, otherwise the whole elevator system will drift away sooner or later. If the center of force lies directly on the geostationary Earth orbit, the anchor has not much to do. But since this cannot be exactly accomplished all the time, it is better to have a fixed point. One possibility is a movable platform like a mobile oil platform would be. On this way, the anchor can be moved in order to dodge space debris or meteorites. Such an approach is preferred, since most of the equator is just ocean. Another idea is not using one anchor at the equator, but two anchors or more with at least one built at each hemisphere. In this way, they forming triangles with, for example, a space station at the geostationary Earth orbit. This will not only make it possible to have spaceports directly near big cities, but also connect them over space. Space elevators would not only benefit to be built on Earth. As the gravity, for instance, on the Moon or on Mars is lower, it is even more simple to build one regarding the tether constraints. Materials, which have not to be that strong, can be used. Building these on other celestial objects, they make it simpler to, for example, deliver cargo to the surface and back. But building a lunar elevator is not as simple, because the gravitational sphere of influence of the Moon is smaller than the altitude of a geostationary lunar orbit would be. If placed in such an orbit, the gravitational force of the Earth would significantly change the course of the counterweight of the lunar elevator. The trick is to use the Lagrange points instead, since the tidal forces of the Moon force it to face always to the same side of the Earth, and thus also to the Lagrange points. In this way, the counterweight will float in one of these points and is still geostationary to the lunar surface. As mentioned earlier, all this is not only a theory. Until today, several tests were already made by performing various competitions with prize money to win, such as were part of the Elevator 2010 contest. Breaking down into different topics, teams competed in this contest to build the strongest tether or to develop an effective way to wirelessly transfer energy. Also, the Japan Space Elevator Association conducted climbing competitions in August 2013. Other competitions are the X-Prize Cup, the Elevator Games, and the GS ETAC, of which some of them were held not only once. The goals were different, from reaching a specific height of a climber or the highest velocity to just making the strongest tether. But also money got provided to write a paper about the feasibility of the space elevator, such as the one from Bradley Edwards. The contests just named do exactly state where the current barrier is to build a space elevator nowadays. We have to make sure that the tether is strong enough to withstand all the applying forces. This includes forces coming from space debris or meteorites. So either way, we have to create the ability to dodge this threat or shield the tether in a way that it would not break on an impact. This also counts for the climber itself. Not only the space debris is a problem, but spacecraft themselves. All spacecraft which will reach an altitude of the perigee lower than the space elevator's countermass have to be redirected or removed from the orbit. Or a way of avoiding or dodging these spacecraft has to be implemented. Also, what happens if the tether breaks? It depends on where the cut occurs. If the cut is near the anchor, the counterweight will fly away within its orbit with the tether. If the cut happens near the counterweight, it will enter an elliptical orbit and the tether will wind itself around the Earth. Since the tether is very light, the tether will fall down very slowly back to the surface. If we want to transport humans with a space elevator, the protection mechanism against radiation have to be applied too. This will make the climber heavier, thus also reducing the maximum possible payload it can lift up. Another point is legal. One of the major issues is that the possibility of collision avoidance of prior launched and still in orbit satellites has to be legally proven. The paper of Edwards states that this is technically possible for sure, but to put this through is another barrier which has to be worked out.